Okay, you want to, we're going to give everybody about 2 more minutes and then we'll start. Okay, so I actually managed to get myself on another account. So it should be fine. So now I see where the slides are. Okay. And I see all the participants. The fun part of having more than one screen. I want to get rid of this thing. Good. Yes. Okay. I think we can start since we have a pretty full agenda. This is computing in the network. This is our interim meeting, and Jeff is on. Eve has been ailing, I would say. I hope she can join us later, but she sends her best. So this is the note well, which everybody knows very well. This is the policies, essentially, I think what's important is the anti-harassment, I think for me. And also for a lot of people, it's the question of patents. So I think this is also very, very important. If you have some information in the presentations that you do today that you think is covered by patents, please make sure that they're disclosed. I will not, I'm sure I'm not going to have any information here that's not there, but I think it's important. And I think it's been also an issue with this group that it is, I think, very important that this is a research group. We're not there to do standards. And you will see today that we have a large amount of, most of the agenda is on research issues and projects and new ideas. And I think this is what we want to encourage and continue encouraging. And I know Colin likes when I say this, but we also invited today a lot of people who presented in other conferences, and we were happy that they agreed to share their work with us. So I think it always is good to expand the collaborations and the participation. And I think in our case, we're very, very lucky that we are very much in a rapidly expanding, essentially, field, and that we are very lucky to be there. And you want to take over, Jeff?
Okay. Hello, everyone. So today we will start from 2 papers. First one is trial, and basically it's proposing a new programmable hardware like Tofino, but it's more similar like the chips in the routers in the internet. So that can be very interesting. And the second paper is distributed coordination for in-network computation. Actually, that was introduced to in ASEAN conference last week, I believe, and that's quite relevant to our group. And then the following three presentations were proposed to last IETF meeting, but we didn't have enough time there at that time, so they will be presented today. So Dirk, Charlson, or Ike, they will give us an update for the use case draft. And Chao Li will introduce a new draft about distributed learning architecture. And Yujing Zhou will introduce some use cases for data population in network. And our last presentation will from Stefano. He presented EIP in one of our previous meetings. Today he will give us some update EIP in context of also machine learning. Okay. Yeah, that's the agenda.
Yeah, we can go to the next one. Okay, so if you hear, it's because you know what that meat gecko is. I asked for a help on the minutes. I may get on the tool myself later when we're done with this. Obviously, we have our mailing list, and we have all the material today online. We have two documents that need update, but they're RG documents, and I'm sure that there's going to be maybe discussion of sending them forward in the approval process after they need their update. We have a new draft today, which is this distributed learning. And then we have this other ton of other drafts that I think we really need to address in terms of making them either, a lot of them are expired anyway. So either we keep them expired or we move forward with them and we can discuss that online. It's not necessary to. Was there a question? So somebody maybe asking a question? No. Okay. And then our milestones. Actually, we're late. On two milestones, which was I think the COVID has hit us in the way. I think the scope is evolving so much that I think the three of us agree that it's really hard to pinpoint. And our milestone review, we're late, and we plan to probably we should do that more online to have more people, but that actually is something that I put on my really to-do list yesterday when I get out of the start of the semester here, and three proposals I'm involved with. But it's really on the to-do, and Jeff, Eve, and I are going to huddle on this and propose something else, and actually propose a new set of milestone that really, really reflect, like I said, the dynamic nature of this field that we're in. You want to add something, Jeff?
No.
No? Okay. So without further introduction, I'm going to end my show, and I'm going to start not unsharing my screen. And unshare is where? I'll unshare my screen, and we can start going through the presentations. And please send your questions on the chat, and I'll monitor the chat also while I try to take some notes. And the first presentation is Trio.
Minglan, can you share your screen?
Yes, let me share my screen. Can you see my screen or is it?
It's coming.
Okay, so this is, you can see my slides?
Not yet.
Okay.
Well, I don't see them.
Okay. Let me try again.
Yep. Do we have to approve it?
Yes.
Yeah, I think I clicked the, yeah.
I've approved
It's
it.
starting now. It's starting now. It's starting. No.
Oh, yeah, one more time.
Okay, so I've
Okay,
approved
yeah.
it, but obviously that's not working. Try again, please. Oh, no, she's back. She's done. But there anyway.
It seems she's offline. It shows.
Yeah, she may have problems.
She's coming
Yeah, I said
again.
we can't. We should be able to load them from the documentation. Okay, so here she is.
Yeah, yeah, I'm sharing again.
Yeah, I know, but it's somehow, what does it say here? I gave you access.
Okay. Okay, yeah. Now I think it should go through. Can you see my screen? Okay,
Yes,
nice.
please. Yes, can go.
Okay, cool. Then I will
Okay,
just get
finally.
started.
Okay, good.
Okay. So, hello everyone. My name is Mingran, a PhD student at MIT with Professor Maya Gobadi. Today is my great pleasure to be here to share our work using Trio, Juniper Network's programmable chipset for emerging in-network applications. This is a joint work between MIT and Juniper Networks. Data-intensive applications, such as machine learning, databases, storage, and data analytics, are the foundation of today's online services. With the gradual slowdown of Moore's law, hardware accelerators are struggling to meet the performance demands of emerging cloud applications. In addition, the amount of computation and memory that can fit in a single server is quite limited. This results in our need for efficient distributed systems for data-intensive applications. The availability of programmable switches, such as Intel's Tofino, has created opportunities for in-network computing to accelerate these data-intensive applications, such as caching, database query processing, and machine learning training. The key idea of in-network computing is to leverage the switch's unique vantage point to perform part of the computation directly inside the network, thereby reducing latency and improving performance. Let's take a deeper look into one of the representative applications, machine learning training. In data parallel distributed machine learning, the deep neural network is replicated across multiple servers, and each server will process a small subset of the entire training dataset. At every iteration, servers will synchronize their model parameters by exchanging and aggregating their gradients to ensure convergence. This step is called all-reduce. One challenge with the all-reduce step is it puts significant pressure on the network fabric because the entire set of model gradients must be exchanged many times during the training process. Recent work, such as SwitchML and ATP, has proposed the idea of in-network aggregation to accelerate distributed machine learning training. Throughout the talk, I'm going to use in-network aggregation as a running example. The fundamental idea of in-network aggregation is to add the model gradients inside the network switches rather than at end host. This can accelerate training jobs with heavy communication overhead. Our results show that The presence of stragglers imposes a practical deployment challenge with in-network aggregation for distributed machine learning. The stragglers are quite common in shared clusters hosting several jobs, where different servers experience uncorrelated performance jitter due to causes like congestion, load imbalance, or garbage collection. When this happens, all other servers must wait for this struggling server. The straggler problem has been studied extensively in the system and networking community, but there hasn't been much attention to straggler mitigation for in-network computing applications. So why is this? The reason is enabling efficient in-network straggler mitigation in Tofino switches is very challenging. To handle the straggler problem efficiently inside the network, the switch needs to perform efficient timer-based operations to mitigate stragglers, such as checking whether a straggling event has occurred or not periodically, and sending notification packet. This is quite challenging because it requires frequent interaction between the switch data plane and the control plane. As a result, today's Tofino-based solutions have no in-network straggler mitigation implemented, and all other servers must wait for the straggler when straggling event happens. In this talk, I will describe TrioML. Sorry, is there some background happening?
Quelqu'un à l'adresse de livraison doit signer pour recevoir l'envoi. Vous ne prévoyez pas être à la maison? Faites le suivi de votre envoi sur fedex.ca et cliquez sur Gérer les livraisons pour savoir si d'autres options sont disponibles.
So can you hear me, or I'm hearing some background noises? I'm not sure what's. Okay, I will
we can
continue.
hear you.
Yeah. So
Maybe you
in
can
this
start
talk,
with the- Okay.
Sorry.
Yeah.
Can
You
you hear
continue.
me? Okay. Yeah, nice. Okay. So in this talk, I will describe TrioML, our proposed system for efficient in-network straggler mitigation. In particular, we can achieve 1.8 times faster training time for machine learning jobs by leveraging Juniper Network's programmable chipset. In the next part of my talk, I will first give an overview of Juniper Network's chipset. Then I will discuss TrioML, our proposed in-network straggler mitigation for distributed machine learning training. And finally, I will talk about our evaluation result. In Tofino switches, the central packet processing element is called pipeline. All packets must traverse through the same set of pipeline stages, independent of the application. Trio is a programmable chipset used in Juniper Network's routers and switches for over a decade. Trio's architecture is fundamentally different from that of Tofino. Trio has thread-based architecture, and the central packet processing element is called packet forwarding engine. For an incoming packet to Trio-based switch, after it enters ingress packet forwarding engine, it will be processed by one of the available threads. Then the packet will be sent to the egress packet forwarding engine and will be processed by another available thread. After the process is completed, the packet will be sent out. When multiple packets arrive, these packets are processed independently using thousands of parallel threads on Trio. Different packets do not necessarily flow through the same physical path on the chip. As a result, Trio gracefully handles non-homogeneous packet processing rate, whereas in Tofino, only line rate processing is supported. With the Trio architecture in mind, in the next part, I will talk about TrioML, our proposed in-network straggler mitigation for distributed machine learning training. To build an efficient in-network straggler mitigation technique, we need in-network straggler detection, which enables the switch to efficiently detect straggler events. We also need in-network straggler recovery, which enables the switch to gracefully serve the job without waiting for stragglers. In-network straggler detection requires timer-based operations based on user-defined straggler timeout. And in-network straggler recovery requires a lightweight mechanism in the switch to proceed the computation. Our system, TrioML, addresses both challenges using Trio's threads. Let's first take a look on in-network straggler detection. As a reminder, back to our running example, to perform in-network aggregation for machine learning models, the servers will send the model gradients to the switch, and the switch will aggregate the gradient result and send back the result. TrioML creates a new gradient record when it receives a new packet from the servers. In normal cases without any straggler, once TrioML receives packets from all the servers and completes the computation, it will generate aggregated results and send back to all the servers. To build efficient in-network straggler detection, our goal is to detect non-responsive servers within delta milliseconds timeout, where delta is a configurable parameter. In the case of straggler event, if server 4 is a straggler, then the gradient record only contains gradients from server 1, 2, and 3, because server 4 does not have a chance to send the gradient from itself. The naive approach for in-network straggler detection is, as soon as new packets arrive, the switch launches a thread and starts a timer to keep track of the non-responsive servers. In this case, the switch will launch a thread and detect which server is a straggler. However, the problem with the naive approach is that it couples the start of timeout threads with arrival of new packets. So the switch will need to create one thread per packet. As a result, this approach is not scalable for large machine learning models. To bound the number of threads needed, TrioML's approach is to decouple the start of timeout threads from packet arrivals. In our design of TrioML, we divide the total gradient records into n groups, and each group is scanned by one thread. We also add a specific recently referenced flag to each gradient record. This flag is set to 0 when the record is first created. Every delta timeout interval, TrioML launches threads to scan gradient records. If the recently referenced flag is 0, then the thread will set this flag to 1. After another delta timeout interval, TrioML launches another n threads to scan the gradient records again. If recently referenced flag is 1, then the gradient records time out, and the straggler is detected. With this approach, TrioML guarantees the straggler detection within delta to 2 delta timeout window. Once straggler is detected, we need a way to perform in-network straggler recovery. TrioML achieves in-network straggler recovery by sending partial aggregation results to all the servers. Prior research shows partial aggregation can achieve comparable convergence performance. In this way, non-straggler servers continue to make progress without waiting for straggler for a very long time. And also, TrioML keeps updating the straggler to ensure the machine learning model is consistent among all the servers. In the last part, I will talk about our evaluation result. We perform training tasks on real-world testbed, including a Tofino switch, a Juniper Networks router, and 6 servers. We compare our solution TrioML to Tofino-based in-network aggregating solution called SwitchML in an ideal environment where no stragglers exist. To evaluate the training performance when straggler exists in the cluster, we followed prior work on straggler generation pattern. Namely, we set 3 possible delay points per iteration. At each delay point, one server slows down with a given straggler probability P, and the delay time will be uniformly randomly chosen between half to 2 times of the typical iteration time. The first result I like to show is the impact of struggling probability on training iteration time. We sweep through different probabilities and measure the corresponding training iteration time. The red line shows the iteration time for SwitchML. As the struggling probability increases, SwitchML's iteration time also increases because the switch needs to wait for the strugglers before generating the aggregation result. The blue line shows the iteration time for TrioML, and the green line shows the iteration time for the ideal case with no strugglers. TrioML is able to maintain the training iteration time close to the ideal case because we have the in-network struggler mitigation to mitigate the effect of strugglers. When struggling probability P equals to 16%, TrioML achieves 1.8 times speed up compared to SwitchML. The second result is time to accuracy improvement with struggler probability P equals to 16%. In this figure, x-axis is the training time and y-axis is the validation accuracy. The red line shows the training time for SwitchML, and the blue line shows the training time for our solution, TrioML. With a moderate rate of strugglers, TrioML can reach the target accuracy 1.6 times faster than SwitchML. We also observe similar gains for ResNet 50 and DenseNet 161. To conclude, strugglers impose a deployment challenge for in-network computing solutions. In this case, we propose TrioML, a novel in-network struggler mitigation system using Juniper Network's thread-based programmable chipset. And TrioML outperforms today's in-network aggregation solution by up to 1.8 times. That's all of my presentation. Thank you so much for listening, and I'm happy to take any questions.
Mingran. Are there any questions? Yes, Jeffrey?
So, Mina, I have two questions, maybe. So, first one is, you mentioned the iteration time. So, it seems it's several hundred milliseconds. So, yeah. Is that a realistic assumption? Or because typical the network delay is maybe several microseconds. So why this kind of assumption is realistic in the data center?
Okay, yeah, I can answer that. Okay, yeah, you can go ahead and I will answer.
The second question is, so please go back to the maybe you can answer the first question first.
Oh, yeah, sure. Maybe I can just go back to the evaluation where the first result shows. So, yeah. So your first question is about the training iteration time. Like it's in hundreds of milliseconds. So to answer this question, basically we perform this training experiment on real-world test bed using a real-world model. And this is the result we get from the real-world model. And also we compare our results to the typical machine learning training work, and we found that the result is quite similar. So it's not an assumption, but it's the result we had from the real experiments.
So can you go back to previous slide? I noticed you have a set in your setup. Yes, so you introduce some staggerer, right? So yeah. That is the time scale of that staggerer is iteration time similar to iteration time. So my question is that realistic assumption?
Yeah, so the structure generation pattern, the structure generation pattern is that we follow a prior work on the struggler. We follow a prior work on struggler, and we follow their approach to generate the strugglers. It is a realistic assumption because the typical iteration time is in the next slide, and basically we just choose the struggler time to be half to 2 times of the training iteration time. This is based on prior machine learning work. And also, so you think it's too large or too?
Such long or large, but the stagger in realistic maybe is not the same scale of the iteration time, because
I see. So
maybe
you are thinking the struggler is mainly caused by network delay. Is that your point?
Yeah.
Oh,
yes.
yeah. So basically, the struggler can be caused by many reasons. It's not simply about network. There are also something can happen on the struggler operating system, such as the struggler is busy doing other tasks, or the struggler is doing some garbage collection task on the server. So these are all the reasons that can cause the struggler. It's not simply about the network delay.
Okay, I see. So my second question, thank you. The second question is about the background traffic. So in your experiment, are there any background traffic, or it's just this single application?
What do you mean by background? You mean other tasks are happening at the same time?
Yes.
Oh, yeah. So in our experiment, we are not having another task happening at the same time. But in realistic setting, it is possible that multiple tasks are running at the same time. And this is when our structural mitigation effect can benefit the real system.
Okay. So I have no further question. Thank you. And there is one question in the chat channel. So can you see it, or I can read it out?
Yeah, let me check.
So, which improvements are related to the specificity of the chip, and which are generic?
So for the improvement we are getting from the structural mitigation, it is quite specific for our approach of mitigating the structural effect. So as you can see in this evaluation result, the red line is the in-network aggregation for using the Tofino switch. And the blue line shows the iteration time based on our chipset. Our main benefit comes from our ability to mitigate the struggler inside the cluster, whereas in other solutions, the Tofino-based solutions, it is very challenging to implement such mechanism. So the improvements are basically coming from the struggling mitigation we have in the system.
And so thank you again very, very much for this presentation, and we can move to the next one.
Yeah, thank you.
Thank you. And the next one is Dicer, which is another application, of course, in network computing. And I will let the authors present. Who's presenting? Oh, it's Uthra who's presenting. So I will let Uthra presenting. Thank you.
Hello, am I audible? Hello?
Yes, we can hear you, please.
Okay, perfect, thank you. So, good evening, everyone. I'm Uthra Amlahan, a PhD student at Robert Bosch GmbH with Technical University of Munich. And my research topic is currently focused towards orchestration solutions for ICN-based in-network compute systems. Today, I'm going to present Dicer, which is a distributed coordination solution for orchestrating in-network computations. The traditional internet was originally designed to enable communication between stationary nodes, and therefore it adopted a host-centric communication model. In order to communicate with a node and retrieve a piece of information, one first needed to establish a channel to the node, providing this information. So information-centric networking architectures, such as name data networking, shifts this focus from the host providing the data to the data itself, and hence the name information-centric networking. This enabled end users to not only address and access data directly using name-based access mechanism, but also resulted in a loose coupling of data to the host. Other features of ICN include inherent multicasting capabilities by interest aggregation, in-network caching, flexible hop-by-hop routing, and so on. So information-centric networking therefore provides access to data instead of the host. Now, name function networking further extends name data networking, or NDN, by enabling end users to request not just static data, but dynamically computed results. So consumers request for execution results with the help of defined workflows that help to structure the request name. NFN uses this underlying NDN's forwarding principles along with resolution strategies which resolve the function request and help forwarding it to the suitable execution nodes. The default resolution strategy in NFN is find or execute. The nodes identify the function and data objects from the request and decide to forward the request if the node has neither data nor function. So this can be illustrated with the help of the figure here, where NFN node 1 forwards the interest I1 because it has neither the function nor the data for executing. If on the other hand, if there are few missing components, the node initiates a fetch operation to fetch these missing components. For instance, the NFN node 2 here initiates a data fetch operation because it has a function F1, but is missing the content of data D1, and therefore sends a data drag operation. So if it is missing function, then it sends a code fetch and so on. The node decides to execute a function if and once all the required components for computing the result is available. So in this case, NFN node 2 here executes F1 as soon as D1 reaches node 2. And the result of this execution is now again sent to the compute consumer. So although this decentralized NFN resolution engine performs per packet decision, which results in timely resolution of requests, there are still some limitations. For instance, the structure of the workflow defines the path taken by the interest or the request. So the consumer who defines these workflows is often unaware of the characteristics of data or function while creating these requests. And this could result in a workflow taking a different path that is less efficient when compared to the path it would have taken had the same request been structured a little differently. Additionally, in order to make prompt decisions, the resolution engine restricts the amount of information it processes to the local knowledge of the node, and therefore does not consider the topology or the neighboring node characteristics while making these forwarding decisions. So this could lead to suboptimal forwarding decisions, especially while considering decomposition of functions. So some such suboptimal decisions could be improved by enhancing the knowledge scope of the nodes while making these decisions. DICER is a distributed coordination solution which targets this enhancement of local knowledge scope used in decision making and improve the suboptimal resolution of NFN. So DICER retains the NFN forwarded at all compute nodes. Additionally, DICER establishes synchronization groups where all the nodes in a group exchange their state information with each other. This added knowledge of the surrounding nodes would then help improving the resolution decisions taken by NFN. The figure shown in this slide comprises of 3 nodes, NFN nodes, A, B, and C, and the blue circle around the node shows the knowledge scope of the node using which the nodes, which you can see that does not extend beyond the node. The queue next to the nodes B and C refer to the execution queue that the node is presently handling. When a compute request reaches node B, the node decides to forward the interest upstream towards node C due to lack of data and function, even though it has a compute resources that can be used for execution. Node C, on the other hand, despite holding the necessary components, does not have the resources to spare for the execution of this interest. Hence, the interest is added to the execution queue, resulting in further delay in the response. With dicer, we now group nodes B and C together, and the nodes periodically exchange information about their state with each other. In this case, node B is made aware of the execution status and compute resource availability of node C. The extended knowledge scope around node B and C is represented using this brown shaded region around the nodes. Once the nodes synchronize, the nodes can coordinate with each other, enforcing some decisions that alter the resolution decisions taken by their respective NFN resolution engines. So in the third figure here, node B realizes that node C is overloaded with interest and performs some fetching operation of function or data. This enables the node B to now participate and share some of the load at node C and reduce the latency in responding to the computed result to the consumers. There are still some challenges and open questions that needs to be answered in order to realize dicer. So how do we group nodes? When and what information do the nodes synchronize with the members of the group? What kind of coordination decisions should the nodes take with the collected information? And how do we handle the network overhead that arises out of such periodic synchronizations? In order to answer these questions, we split the concept of dicer into 4 phases, namely neighbor node discovery, synchronization group formation, synchronization, and coordination. In the upcoming slides, we present in detail each of the 4 phases. The first phase is a neighbor node discovery phase. This is dedicated for the nodes to understand the network topology and the static characteristics of the surrounding nodes. And in order to accomplish this, we take inspiration from the name linked state routing protocol, the NLSR protocol, for sending periodic hello messages from every node. These periodic discovery messages are broadcasted in periodic short bursts. And in order to curb or restrict the flooding of network links with such discovery messages, we use interest hop limit to a certain range within which the nodes need to be discovered. Every node receiving the discovery messages would then respond with the static configuration information, such as compute configuration, network link capacity, hop distance, path latency, and so on. The table in this slide is an example of information data procured at node N1, at node 1 about the other nodes. And once the nodes are discovered, the periodic phase is now used to identify nodes entering or leaving the discovery scope. The next phase is the synchronization group formation phase. We define synchronization group, denoted by SG, by 3 parameters, namely members of the group VI, the synchronization interval or frequency TI, and the information synchronized, which is PI. One could theoretically group every node in the world into a single synchronization group and synchronize it on extremely fine details at very short intervals. However, this is not practical due to the network overhead in sharing huge volume of data and the processing overhead for making coordination decisions. At the same time, restricting the group size and the information may not help in bringing quantifiable improvement over NFN. Hence, we are employing multiple synchronization groups of varying size, information, and frequency. The figure here shows 3 different synchronization groups, SG1, SG2, and SG3. SG1 is a group of nodes 1 hop away. SG2 groups nodes that are up to 2 hops away, and SG3 groups nodes that are 3 hops away, and so on. The size of the group SG1 is smaller than SG2, and SG2 is smaller than SG3, meaning the number of nodes in the group is in the increasing fashion. And the darker the shade of gray is, fine granular is the information synchronized. So as the size of the group increases or as the distance from the node increases, the amount of information shared is reduced to just the crucial information, the crux of the information, and the synchronization interval is also reduced. This helps in gaining information across a large scope while maintaining the network overhead under control. This slide shows the sequence of interest data exchanges that happens in the group formation phase. The synchronization group formation proposal interest is initiated by every node targeting the discovered nodes and inviting them to join the group. The nodes receiving the interest would then respond with a follow-up interest requesting for other information pertaining to the sync group, such as the other members of the group, the scope of synchronization, periodicity of synchronization, and so on. If the nodes do not detect any redundancy with already established groups, then the nodes respond with an acknowledgement for joining the group. And on discovering new nodes to be added to an existing group or removed from an existing group, all the other group members are notified as well as part of the group formation phase. At the end of group formation, where all the nodes have been created at the nodes, all the groups have been created at the nodes, each node performs group optimization to detect and avoid any redundant synchronization happening within these nodes. An example of group optimization scenario is shown in this slide with a 5-node network. So the node 1 forms two groups, one group with nodes 1 hop away, that is with node 2 and node 3, and another group with nodes 2 hops away with node 4 and node 5. Similarly, with respect to node 4, it also forms two groups, one with nodes at 1 hop distance with node 2, 3, and 5, and another with nodes at 2 hop distance, that is with just node 1. Here, the 2 hop group at node 4 is redundant, as all members of this group are already a subset of 2 hop group from node 1 and therefore is completely removed. Node 4 also refrains from fetching the updates from node 5 in the 2 hop group of node 1, as they already fetch more fine detailed information as part of the 1 hop group that is formed by the node 4. Additionally, nodes belonging to multiple groups of the same scope also avoid fetching the changes twice per synchronization. For example, here node 2 and node 3 both belong to 1 hop group from node 1 and node 4, and hence do not fetch the change updates if already obtained from the other group synchronization. So such group optimization is mainly focused on trying to avoid any additional network overhead from synchronization occurring from redundancy, and therefore it detects such scenarios. The next phase is synchronization phase. We adopt the application dataset synchronization protocol called the state vector synchronization, which is SVS, which was formally developed for synchronization in distributed applications with several participants. An example of one such application is the Indian chat application. The SVS data model is based on vector clocks. In this slide, we show SVS in action for the network shown here with 3 nodes, user A, B, and C. The change updates at each node is mapped to a sequence number, and this sequence number is published as a part of change notification. For instance, there is a change update at user A, and the sequence number is now incremented from 50 to 51. This changes corresponding to 51 needs to be updated to other users in the group. This is done with the help of a change notification, which is a sync interest initiated by user A. The structure comprises of the group prefix followed by the state vector representing user A's knowledge of states of all the users in the group. The sync interest is now multicasted to all other members of the group. Each group also holds a local data store which records the history of changes at each member of the group. The slide here shows the data store at user B and C. By comparing the state vector in the change notification with the local state in the data store, they detect if there are any updates in the other members in the group. So now they detect that there is an update in user A that they are not aware of. In order to fetch the latest change updates from user A corresponding to sequence number 51, both user B and user C initiate the fetch operation. Once the corresponding data packet reaches the users, they update their data store such that the local state is synchronized with the group state. Therefore, in order to fetch each change update, it costs approximately 3 message exchanges, 1 sync interest, 1 fetch interest, and 1 fetch data. The synchronization phase can be invoked either periodically, where the nodes publish a sync interest at fixed time periods, or it can be invoked in an event-triggered fashion, where each change is an event triggering synchronization. In DICER, we implement 2 types of synchronization groups, grouped based on hop distance. The 1 hop synchronization group at each node groups nodes with 1 hop away, while the 3 hop nodes scope extends to 3 hops. The node within one hop group share fine granular information of state, such as node's resource utilization, functions instantiated at a node, functions requested at a node, list of unresolved function requests, the current execution queue, and so on. Since the three hop groups are larger in size, the synchronization information is aggregated, and each node shares a cumulative knowledge of itself with its one hop group, which we refer to as a zone. That is, each node shares the cumulative knowledge of the network zone it belongs to. And examples of those could be the average resource utilization of a zone, the most unresolved function or most popular function at a zone, and so on. The synchronization interval for one hop periodic synchronization is closer in order to enable the neighboring nodes to react quickly to the changes in the neighborhood, while the three hop synchronization is invoked at larger intervals so that the neighboring zone is prepared to handle the gradual changes in the network across a widened scope. After synchronization, the coordination decision making phase begins, where each node aggregates all the information collected from synchronization. With the information, the node enforces some changes locally that alters the forwarding behavior of underlying NFN resolution engine. Each node identifies whether it has the necessary compute resource available for executing function requests. If the node can spare some compute resources, then it identifies any busy neighboring nodes, which is congested with requests, and the list of unresolved functions at such nodes. This list is then sorted in descending order to ensure that the most popular unresolved function is resolved first or instantiated first, and the free nodes fetch such functions and instantiates them, resulting in a load balancing effect by sharing some of the compute load from the busy node. On the other hand, if the node is facing a high compute load already, it looks for any idle or less frequently requested functions that can be terminated. Such functions are forwarded upstream at the cost of increased network consumption and latency in responding to these requests. Now, we implement all the phases of DICER and evaluate them using NDN-SIM, which is an NS3-based simulator. We implement the INC-SIM module, which simulates the behavior of NFN resolution engine at the compute nodes. DICER is an application running alongside NFN, taking care of the phases such as neighbor node discovery, group formation, optimization, synchronization, and coordination. The network setup comprises of a hierarchical topology of compute nodes and consumers. The simulation parameters that we use is presented in the table shown in the slide. We generate the compute load by allowing consumers to request for function execution over different data components. And the following slides would present the different evaluation metrics and performance of DICER against NFN. The first evaluation metric is the orchestration map. So orchestration map shows the function placement at each node in the network topology. We also implement the next fit decreasing heuristics, which sorts the function in descending order of popularity and places them at nodes closest to consumers and progresses upstream. And this heuristic does not replicate instantiation of popular functions at multiple nodes. Now we compare the orchestration map generated from DICER and NFN against that generated by NFID. And on the x-axis, we have the increasing number of compute nodes in the network. And on the y-axis, we have the number of functions placed at these nodes by the different solutions. With NFN, the number of functions instantiated is less compared to that of DICER and NFID in an imbalanced load scenario. So by imbalanced load scenario, what I mean is that in a network setup, half the nodes face high compute requests while remaining half of the compute nodes are pretty much idle. In this case, the nodes which do not observe any compute load in NFN remain idle, and those nodes with high compute load are congested with growing execution queue. On the other hand, with DICER, since the nodes are more aware of the network state in the zone, it identifies and instantiates more popular function, bringing up a load sharing effect. Additionally, the DICER coordination algorithm also ensures replication of those popular functions with a high number of requests that cannot be handled by just a single instance of the function running at a node. So DICER also takes care of replicating popular functions. We also evaluate the reduction in completion time with DICER. So completion time is defined as the round trip time from the compute request initiation of the consumer until the corresponding data packet with the result reaches the consumer. We tune the imbalance factor denoting the load distribution at the compute nodes from a balanced load where all the compute nodes in the network face equal compute requests to an imbalanced load, which is IBF equal to 1, where the load is just on 50% of the nodes. On the x-axis, the number of unique functions in the setup is increased, and on the y-axis, we have the completion time. We observe that in a balanced load, NDN already performs well with identifying and instantiating the needed functions in the compute nodes. But in an imbalanced load situation where half the nodes are idle and other half of the nodes are extremely busy, DICER brings down the completion time by utilizing the compute capacity at the idle nodes. The next evaluation metric is the network overhead of using DICER and its effect on the scalability of the solution. So in this graph, on the x-axis, we have the network compute scale denoted by the number of compute nodes, and on the y-axis, we have the generated network traffic from DICER synchronization. We employ different synchronization intervals starting from 2 seconds up to 50 seconds, and we see that the network overhead shows a quadratic relationship with the network scale as well as the synchronization interval. Group optimization to an extent already helps curb this overhead to a certain extent, but there are also other ways to reduce the control traffic, for instance, by employing event-triggered synchronization in a passive network, or one could also employ partial synchronization or one-directional synchronization, where nodes with high centrality degree collects information from surrounding nodes and enforces not local but zonal decisions. And the nodes which are not well connected do not get any updates from the other nodes, and this kind of reduces the synchronization overhead even further. So this brings to the conclusion of my presentation of DICER. Summarizing, we presented the default resolution strategy of NFN along with its limitation, followed by the 4 building blocks of DICER concept. And this was followed by a brief overview of the evaluation metrics and performance comparison of DICER against NFN. And as part of future work, we intend to enhance the coordination algorithm to operate on the objective of achieving joint optimization of compute and network resource utilization, as well as minimization of completion time. Currently, the coordination algorithm only focuses on function placement, and we next intend to also include the characteristics of data objects and placement during decision making. Here are the references used in this presentation. Thank you, and I'll be happy to take up any questions.
Are there any questions? Okay, there's none. Anyway, questions can be sent to the chat or be sent to the list. Well, we're on time, which is great. So next one is Dirk, I think, if you are presenting. So did you have a question, Dirk, or you're just presenting? Okay, Dirk is presenting, and it's the use case update. Thank you.
Hi, sorry, a bit slow here with my clicking the buttons, the various buttons here as I wanted to present. I wasn't entirely sure if this was the last version that was on the data tracker. And I swapped the presenter. Ike and I did a double play, but I ended up doing the presentation. Yeah, this is about the use cases for in-network computing. You'll notice, and I'll come to this later on at the end, this is an expired draft. Marie already mentioned that, so you can find it in the archive at the moment only. Clicking on the yes. So the purpose of the draft is to go after, what the COIN Charter talks about in scope number 2, research and use case-driven requirements analysis, benefits of the type of networks, of these networks from internet-driven functionality. That's all text that's written in the charter. What we've done so far with the draft was to collect use cases. Recently, in the most recent iterations, we worked more on structuring them. The draft, if you follow the draft in the past a little bit, it had an organic growth. It's a emerging of several activities into a single collection of use cases. But the structuring then was looking more into providing insights into those benefits, research question opportunities for COIN to go really more on what the charter was asking for as a goal. We started with when it was adopted finally as a research draft, and we are currently at version 2, which is the one that expired. But in version 1, we already started regrouping the actual use cases as a result of the adoption. We have now 4 major groups, which are the 4 main sections, which are looking at new COIN experiences, new COIN systems, improving existing COIN capabilities, and enabling new capabilities. And we elaborate in these sections a bit what do we mean by that. We also try to sharpen and tighten up the taxonomy. I'll come to that in the next slide, and also prepared and started the analysis on research questions and requirements. I'll come to that as well. So there was quite a significant change when we actually went to the adopted draft level. So this is the current structure, and that's the same for V1 and V2. We just added more cases, nothing really that did change. This is the use case regrouping that I mentioned. So the main sections 3, 4, 5, 6 are the 4 groups I mentioned before. We yet again got another use case. So Xavier joined the draft was a new use case in virtual network programming. There was another one. That was the latest one that we added. We also had, where is it up there? The personalized interacting performing arts as an example that we added with Miguel and David, who joined, I think, also around the same time. So Marie-José joined, I think, with the extended reality. So that's what I mean. It was kind of like bringing various views and various people together that in the end ended up on the author list. As it started with the analysis in V2, so that's the latest section, number 7. And we also try to, in the meantime, to partially align our terminology with the other draft that Marie-José mentioned, the Kutcher's draft that has also expired in the meantime. The terminology, as I said, we introduced language and tried to also adjust all of the use cases to follow the same language, given that they had grown organically. There was a bit of a language mismatch, which we tried to smoothen out a little bit. So we introduced these type of terms that are explained in the draft: COIN program instance, a function, capability, etc. These are the definitions from the draft. Excuse me. And the green ones we try to align with Dirk's draft, and we also introduced a few new ones, the COIN experience, the COIN capability that I mentioned, also in the regrouping of the use cases that we utilize. We also introduced kind of like the devices we're using, PND, a programmable network devices. It's kind of like the term we introduced for something that is programmable using something like P4 or similar, right? Then we also restructure the use cases. So we try to follow the same kind of taxonomy in all of them so that you can hopefully read them in a very similar manner. So there's a link to the category in the description. The description is trying in a relatively prosa language to outline what it really is that this use case provides as an experience and characterization, what are existing solutions to maybe do parts of these use cases, in some of the use cases, parts or almost entirely. What are opportunities, and we split up the opportunities in the research questions in one of the latest iterations, and then we also added requirements for the account capabilities there. And this is, as I said, all try to pull this through every single use case that we described. I think we've done a quite decent job, at least, to follow that taxonomy, but there are still cases where we need to maybe smoothen it a little bit more. We started, as I mentioned, in V2 with the attempt of an analysis. So for that, we used and we had a couple of separate meetings between the authors to think about how can we structure research questions along various categories. And some of you who may recall material I presented something similar in the other interim we had, losing a bit of track of time. I think that was in spring this year, right, when we had the other interim, on how could you look at the various things that we're talking about. So, you can see visions for COIN at the bottom, enabling technologies, distributed computing framework, applicability areas, and we adapted this kind of way of looking at COIN in order to structure research questions along those different categories, right? The requirement analysis is something we intended to. We have requirements in the actual use cases, but we haven't really looked at them coherently. That's the part that's still missing. That's an empty section at the moment. So the next steps where we are that we would like to do, well, the first observation coming back to this, the draft has expired. There was a notice recently, and there was a discussion among my HSA, Ike, and myself. What should we do? At the moment, we let it expire in order to present this to the working group, in order to come to the questions in the next slide, right? So we would need to resubmit a new version. That's the first step. There is work in the draft that could be done, finishing to align the use cases. As I said, there's still some bits and pieces and corners where we need to smoothen the taxonomy a bit. It's a huge task that needs to be done. Aligning the draft with the terminology that we try to introduce, and also obviously also agreeing on the terminology if possible. The analysis part, condense the opportunities, research question, all this kind of things. But that brings me to the questions in the first place. So there is work that could be done if you wanted to. The questions that I have to the community, the working group is, well, first, do we want to collect a terminology that's emerging from this draft and also trying to, aligning with the Kutcher's draft? Where do we want to collect that? Is that a good place to leave it in this draft, or do we want to have this somewhere separate? That's the first question. We also looked into, should the analysis really be part of this document? We started with the analysis because we felt that there's material in there that could really help us to make sense of the discussion. Or do we want to maybe finish this document and do the analysis in a more thorough manner, maybe in a different document, right? We could keep this purely at the use case level and leave the analysis for a separate document. That's another question to decide on. But I think the most crucial one really is, given that this draft has expired, do we want to see this work continued? I mean, the drafts are available, they're in the archives if you want to read them, but do we want to have the work continue? Do we want to have a last call for publication, considering the editorial questions that are asked around analysis? Do we want to continue? And then obviously the question inevitably is, are there any other contributors that would help us pushing the work forward? And with that, I think there's a question from my HSA as one of the co-authors or as a chair, I don't know. Thank you very much.
Is more as a chair than a co-author. I think it relates to your questions, and of course we could move a lot of that to the list, but I think collecting the COINRG terminology is a good idea. Maybe it would be maybe better to put it in a small draft and making it on its own. A lot of groups have ontology drafts and RFCs, so I think that would be anyway. But I think, and others can disagree. I would say the analysis, I agree with you that it maybe should be out. And I think it's important to have the work continued. And this is me as a chair now. I know I'm also a co-author, but I think it's an important topic because of how dynamic the field is, and the use case that are in there have some kind of also of a historical nature. We started this a very long time ago, and I think it evolves with the field, and I think would have like some kind of a good overview of how this started and where it's going. So yeah, so this is me as the chair. I think as a co-author, obviously, I'm open to continue helping with this, but yeah, so those are my comments. Any other people? Questions? Comments? Okay. So thank you, Dirk, and thank you everybody for presenting this. And I think I'm lost in the agenda, but the next presentation, is a new draft. from Zhao Li from Beijing University of Post and Communication. And it's also about some ML related work. So Zhao, you want to present? Are you there? Yes. Okay, cool.
I'm sorry, I can't find my slides.
Oh, they should be there.
No, it's not mine.
I gave you the share. I gave you the control.
Okay. So okay, sure.
Oh, there we go.
Okay. Hello, everyone. My name is Charlie, and I'm giving a speech on behalf of the authors for our work. Topic of my speech is distributed learning architecture based on edge cloud collaboration. Oh, sorry. Okay. IoT-based artificial intelligence is an important application scenario of this work, which requires a large number of artificial intelligence models to provide service for IoT device. The IoT architecture is shown in the figure, which is divided to cloud layer, edge layer, and device layer, and they have their own jobs. This is my motivation with the development of 5G technology and the popularization of IoT. Massive edge data is graduated by the disappear post mobile terminals and IoT device. When facing the training requirements of artificial intelligence models, the edge computing and the cloud computing have their own shortcomings. So distribute model training architecture based on edge cloud collaboration has become a feasible scheme for artificial intelligence model training. Okay, here is our works. So first, I will introduce besides technology, the model training slide as shown in the figure A. Since each layer of an artificial intelligence model have a independent input and outputs, a model can be split into multiple sub models for independent training, where the training layer that links the submodels is called the segmentation layers. This method can provide the besides for edge cloud collaborative training. So the training this is the entire training process is shown in figure B and figure C, but it seems some mistake. The edge node sends a model training request to the cloud nodes. After the cloud nodes received all training requests from the edge nodes, it prepares for model training, which is divided into data standardization and the model determination. In the model determination, the cloud nodes determine the model architecture according to the training task and send it to all edge nodes. And in order to reduce the amount of the computing in the training process, they said it need to be reason before training, the standardization master is determined by the cloud node. After the preparation of is complete, enter the model training stage. In order to ensure the quality of the model training, it is necessary to ensure the consistency of training delay and the consistency of the model transmission delay. The training delay and the transmission delay are set by cloud nodes based on experience. In terms of the training delay, combined with the model splitting and the computing power network, can calculate the training time of each layer of the models, and the number of layers to be trained by each node is calculated according to the training delay. At the same time, it's also possible to determine the size of the data volume of the segmentation layer and then reserve boundwise for the model transmission in advance. After the edge node finish its training of prepared training model, it sends the segmentation layer of the prepared training model to the cloud node. After receiving the signatory layer of the model, the cloud node completes the subsequent training of the model and then updates the model weights. So far, a round of model training is complete, and after each 5 rounds of training, the cloud node generates a global model through the distributed learning, such as the fund-rotated learnings, and the edge node continue to train according to the global model until the model accuracy meet the requirements. And there is some simulation requires. It show our architecture can improve the accuracy of models and reduce the computing pressure of edge nodes and improve the QoE of network service. Thank you. I'm over. Thank you.
Are there any questions? What do you want to do with this draft? Because you want to continue it? You want to, yeah, what are your goals with the draft? From moving on now?
I want to prove computing balance. I want to provide a computing balance modes for model training in networks, because because the training besides the cloud computing is need large bandwidth and high energy consumptions. It maybe not works, and besides the edge computing, it doesn't have much computing power, and it can certify the model training requires months. I want to find a balance.
Okay, I think one good thing would be, since this is a new draft, any other questions, things, would be to maybe start a discussion on the list about how this could evolve within the group. So Yeah, so let's do
It's
that.
It's me.
Yes.
Yes. Can you give me my control to share my screen?
I actually.
Oh, okay. Sorry.
Yeah, you have the share. So yes, the next presentation is on new ideas. This first one is for data operations in network, and again, this is from Yujing Zhu from Huawei.
Okay. Thank you. Hello, everyone. I'm Yujing from Huawei. I'm very glad to share my thought about our solution data operation in network. And today, maybe I just pay more attention to discuss some Dawn use case, and I will introduce what scenarios we think Dawn solution can do better than the traditional way, and maybe I want to discuss the in network computing in another aspect from the network practical, and maybe we want to talk about how some in network computing work can work in a real network like data center. Okay, next page. As a first, maybe I will talk more about our motivation. We know that the recent research has shown that the network device undertake some computing tasks can greatly improve the overall network and application performance in some scenarios, like we talked about, like the first presentation we talked about today. So we think that the Dawn research should pay more attention to some scenarios where the data operation are required to be done at a synchronized node, while the operation is simple enough to be done at line speed. That means we think the network device build some computing tasks will not affect the forwarding performance, and maybe it's just a basic and a simple operation. And so we introduce some 3 Dawn scenarios, and we think it will be useful. Okay, the next page. The first scenario is about artificial intelligence scenarios, and we think in these scenarios, the first presentation we talked about a lot. We think the increase the number of the surveys does not lead to a linear increase in a service performance, and we found many ways to solution this question. For one way is we have a parameter center, and for another way is we have a all reduce solution. But for the net reduce or some computing in the network solution, we know that the switch do some aggregation tests, and we know that the switch in the center topology, and the switch will aggregation the message from the distributed nodes. And in this picture, the switch will aggregation the information from the full machine. And we think that this aggregation, so Dawn thinks that the aggregation may be a basic and a simple operation. Like we can abstract this operation like a sum operation. And if we want, so Dawn think the package from the serial machine to the switch, the package will tell the switch should do the sum operation, and they will have a standard practical to tell how the machine packages this computing information. And so Dawn think in a in a data center the data center has a more complete network topology, and not like some simple topology only have one computer switch. And so Dawn, we think we should have a solution to routing the package to the right right switch, and routing the package to the aggregation switch, not the other switch. And this is we think Dawn should do, and we want to discuss in the Dawn. And this is about artificial intelligence scenarios. Okay. The next scenario we talk about is a log task, and we all know that the traditional way the logging task is a very common question in the database, and the traditional way use the log manage. But in the Dawn, we think we can use the netlog switch to deal this task and replace log manage. For Dawn, we think that the log manager can be abstract as a compare and a swap operation, or like the fetch and add operation. For example, we can send the host will send a log message to the netlog switch. The netlog switch can repeat the host whether they can get this log. Maybe it's a basic and a simple operation. So we think the Dawn think the netlog switch can do this, and will have get benefit from this solution. And in the Dawn, we also think we should support the routing solution or other operation and computing information package way. Okay, so next is the sequence, and the sequence is scenarios that the package, the different package should have a message to decide which message is early to reach the to the server. And in the traditional way, we use the global transaction manager, but in the Dawn, we think this operation we can say that is like a fetch and add operation, and we think we can get benefit, and the Dawn switch can do this, and it will become more faster. In the summaries, in my thought, we think the Dawn network cannot support very complete computer operation, and we think some basic application we can abstract to some basic and simple operation, and we think this operation we can't affect the forwarding performance of the data plane, because if we affect the forwarding performance, we think this will be less useful, and we think our Dawn can deal with some bottleneck of the computer operation. So in the Dawn thought, we think we should have a general mechanism to deal with this question, and we should require to tell the switch what to do, and what the package, how the package routing to the right switch. Okay, this is my thought about the Dawn, and we see that the use case we introduced before, we can abstract some basic operation like the sum, the compare and swap, or the fetch and action. Okay, the next page, and this is we think that the Dawn device we can do, and we can consider in the Dawn solution. At first, we think a Dawn network can route the computing package to the right computing device. We think maybe the Dawn network have a lot of Dawn device, but we think we should routing to the right and device, like the aggregation task which the four machine should negotiation which switch will do the aggregation task before. So maybe we think this is the first question. And another question we think that a door operation should tell the device what to do, like start, like fetch and add, and other maybe like some basic operation. And the third is that we should have a structured data description, and we should we should tell the host how to package the computing message. Okay, that's all. For the next step, we will find a solution maybe about the data plan, and we want to find a general way to send computing information in the networks, and maybe we will consider more about how to make this Dawn work in a reality work, like DC, like data center and other, and hope others to join us. Thank you. Thank you. Thank you.
Thank you very much for this interesting presentation. So what do you intend to do about this work in this group? Do you want to write a document? Do you want to continue doing this strictly as a research initiative that you report on to the group, and that eventually you write a draft or something?
Oh, okay. Maybe now maybe I will plan to have a draft in the IETF, because
so you want to do it in the IETF, not in the IRTF.
Yes, because I think I want to find a solution to make some in-network computing work research to work in some like DC center. So maybe I think I will try to work in the IETF, but I hope some member in the COINRG will join us, because I think maybe it's the same topic.
Well, yeah, but you know, the thing will be for you to find the right working group, and obviously this is not something that we do in this group. But if you want to continue at least keeping us informed of the work, that would be nice. And of course, we can, you can do the work also in the IETF. If you want this to become a standard.
I hope others to join us, because our work is just a start.
Okay, thank you very much.
Actually, I have a quick comment about the name. There's some discussion in the terminology. In fact, this is a terminology issue. So, Eugene, you talk about you name it data operation in network, but your three use cases seems very more computing than data operation. For example, the compare and CAS, right? Compare and swap.
Yes.
And fetch and add. Those are typical computation. Sometimes they are called atomic computation in context of MPI or RDMA. I forgot, but that's typical computation. So that's more computation than data operation, I should say. That's a quick comment for the name, I mean.
Yes. In my thought, so Dawn consider is that the application is changed very fast, and we can't deal every complication case by case. Is not a good way to make our research to become to work in some data center. So maybe I think abstract this operation may be a good way. Thank you.
So we have calling in the queue, and Juniper.
Yes.
Yeah, hi. So just following up on Jeffrey's comment, and with no hats, I was a little surprised that the operations was such low level, given the more high level use cases. And it wasn't clear if this was a computation in the network signaling scheme or an active networking scheme that was being proposed. I think it would be good to be clear on the distinction and where this was going.
Thank you.
Hi, can you hear me?
Juniper, please.
Yes, go ahead, Yunxing.
Thank you. I would like to provide a different angle of view. Yeah, it seems there's some lag here. Right. The data operation generally, in my view, is that the data is carried in the payload. So we provide the data, we provide an operations. So we want the switch to operate on the data following the packet, right? So that's why this work is called data operation. The data is provided, and we have some simple instructions, and let the switch do the work. And also, the reason why all the operations are very low level is because we believe that in these scenarios, keeping the task at line rate is very important. Therefore, combinations of various different operations or atomic computations can take much longer time and slow down the whole forwarding thing. And that's why it's very low level operations. That's all. Thank you.
Yeah, I understand your point. From in-network computing point of view, you always need some data for computing, and those data usually also conveyed by some packets. Otherwise, how we can do in-network computing? So it seems that I don't see a lot of difference between these use cases and in-network computing.
Right. Well, the computing always needs some data. Well, the difference is that you fetch data from somewhere else, or the data comes with the instructions, right?
Okay, so maybe we can discuss this further offline.
Yeah, I was thinking maybe it's worth taking this offline or taking it to the list again, because this is kind of new work. It would be maybe interesting to bring into the list. Next, so thank you very much again, Eugene. And so Stefano is now going to present us another machine learning for networking. Actually, this seems to be a theme today. And actually, knowing what I do in the rest of my life, I think it's a theme for many people. So Stefano, please, I will grant you the screen.
Okay, I'm trying to share the screen. See screen.
Yes, you have access. Oh, there we go.
Okay, so can you hear me? Can you hear me? Hello?
Yes, we can hear you.
Okay, thank you. So welcome everybody. So I'll present this update on machine learning for networking use case for EIP, extensible in-band processing. This is a work jointly done by me and some colleague of mine at University of Rome Tor Vergata, then Tushar Swami at Stanford University, and Mohammad Shabatz at Purdue University, and Sham El-Bakouri. So in the previous presentation here at COIN, Tushar and Mohammad Shabatz have presented have presented a solution for per packet machine learning inference using Torus. So in this work, we will extend the Torus solution, which is based on a single node, to a distributed architecture in which we have feature extraction separated from the process of machine learning inference. For this distributed architecture, we need to transmit features that are extracted by one node and should be sent to another node. And we want to do it very quickly, in the data plane, and because we want to keep the idea of having a per packet machine learning inference, that we want, for example, to detect anomalies in a very small time window. And then we thought to use the EIP mechanism to transmit this encoded feature from one node to another. So a very short, in 3 slides, I will just recall the Torus architecture for machine learning. And the idea is that there are several applications of machine learning in networking, like anomaly detection, traffic classification, or congestion control, you see. And all this, most of these applications really are good if they are applied on a packet per packet basis. But usually it's very hard for the processing requirements to do machine learning inference on a packet by packet base. This is why the Torus solution has been proposed. And in this Torus solution, it's a switch pipeline which includes a machine learning inference engine. So the idea is it's kind of the extension of a programmable switch, like a Tofino architecture, in which you have you see the normal packet parsing, the processing of packets based on match action tables. And in addition, in the Torus switch pipeline, there is a machine learning inference engine that can take, for example, classification decision based on the features that are extracted by the previous stages of packet processing. And what has been shown in the Torus in a paper is that this can work at line rate. So it is really possible to apply classification at line rate with this switch architecture. So in the paper, they show a single node model in which you have a single switch, for example, which receives packets at line rate. These packets are parsed and pre-processed because usually you cannot run the inference only based on the information that is contained in the single packet. You have, for example, to do something like collecting per flow features. So you should count how many packets of the same flow have been received in the last 10 seconds. Or you do this. You need to do this type of processing that we call it the feature extraction. Okay, so in the single node model, the node performs the feature extraction using a traditional architecture like a Tofino-based architecture. Then these features are extracted and they are handed over to the machine learning inference engine, which can perform at line rate the machine learning inference. So in this work that I'm reporting, we want to generalize this idea. And we think that in a network context, we can have this approach with a distributed feature extraction and machine learning inference. And there can be several scenarios in which it can be useful to extract some feature in one node, then encode the feature, transmit them to another node that can perform the machine learning inference. And a typical example can be you may have a data center in which you have an aggregation switch, and this aggregation switch is receiving traffic from thousands of servers, and each server has maybe tens of virtual machines inside, and it is not possible for this node to perform the feature extraction for all these flows in parallel, because this requires a lot of state information to do the extraction of feature for each single flow. So there are this scenario in which is very useful to have, for example, on every single server to extract feature. Then you need to transmit the feature to the switch, and because in the switch you have the hardware that is capable of running the machine, the ML inference at line speed. Okay, so this is a more generic vision that we will have some nodes that are capable of extracting feature. They will transmit this feature to other nodes that could be typically switches. These switches are capable of running machine learning, but they are also capable of, again, extracting features. So there could be two levels, let's say, of extraction feature before using the machine learning inference, or even this feature can be evaluated by one node and sent to another node for further processing. So this is a rather general model that we are proposing. So now there is the problem how we can encode and transmit these extracted features from one node to another. And now the solution that I have presented in a previous presentation, which is called extensible in-band processing, comes into play. So I already presented that with extensible in-band processing, we want to put information in the IPv6 header using, for example, a hop-by-hop option. And this is a generic container for several use cases that I have mentioned in my previous presentation. So this encoding of feature for machine learning can be just seen as a new use case for the proposed EIP mechanism. And in particular, we are defining a record that we call the encoded feature representation, or EFR record, okay, that can be transmitted as an information element inside this proposed EIP option. So basically, we have a framework which is generic, it is extensible, and is used to transmit information in the data plane among different nodes. And in this case, we are exercising this generic mechanism for this new use case, which is the transmission of the feature for a distributed machine learning solution. Then we are making some consideration that the encoding of this feature needs to be very, very efficient, because we are adding information in the data plane. So we prefer to have a representation in a record, which is just a plain array of bytes with no explicit tagging of the features. And so, of course, we need to find an agreement between the sender and the receiver of the information to specify what is the content of the features that have been transmitted, because there can be different applications, different anomaly detection scenarios, and so the set of features that could be transmitted can change. And so we are defining this this simple solution that there will be some identifiers agreed between the sender and the receiver, and this identifier will specify which is the structure of the record that is transmitted. So, for example, if we have a given identifier, then we are transmitting this feature, number of packets per flow, number of bytes, and for each of these features, of course, we know what is the length of the information that is encoded in this record. So we can discuss how to propose a standard, or rather a framework. So we don't need really to go with a standard in the complete meaning. The point is that okay, we want a kind of lightweight standardization. We believe that we do not need to standardize the content of this record. So the different application will be free to choose which feature needs to be transmitted. So we want to leave innovation open, of course, in this exchanging of feature. But maybe it can be useful to standardize, to use a common framework to exchange these EFR records among the nodes. And in particular, we think that this could be a good use case for the EIP option to define an information element that basically just includes an identifier of the record, and the record itself with the bytes of the features that have been extracted. Okay, so this is a very early, this is an update, and it just includes very early ideas. And the idea of distributing the feature extraction and the machine learning inference open up several research issues. So we are just starting this activity, and so we welcome comments and discussion on this on these ideas. That's it, and I'm open for questions. Thank you for your attention.
Yes. So, are there any other questions? So, what do you want to do with this work?
Sorry, with this.
Where do you want to bring? You want to continue doing this work outside COIN, inside COIN? What do you want to do? And Jeffrey, you're next.
So yes, I like to. We are now working on a position paper describing these things, and then I will extend the EIP draft. We have some draft of EIP that I will include the description of this use case, and I'll be pleased to submit these updates when they are ready on the mailing list of COIN and receive comments. And I think that this is an example of the feature extraction in particular is an example of a processing that is done by inside the network by the network nodes to extract this feature. So I believe it's relevant to the activity of this group, but of course I'm open to comments and about this.
Yeah.
Okay, Jeffrey.
Yes. So first, I think this is quite interesting topic because Stefano is talking about how AI can be used for network. All right. So previous several presentations or talks are discussing how network for AI. But I have a question for you, Stefano. So you try to separate the feature extraction and machine learning influence.
Yes.
But my understanding about the deep learning is that usually they integrate the representation learning inside. So those feature extraction are some hidden states inside the machine learning model. So my question is, do you have some specific application, specific use case or solutions so that we can separate feature extraction?
Yeah, this is a very interesting question. Yeah, I think that the networking use case has these specific characteristics that may be made different from a traditional machine learning, because maybe in traditional machine learning, as you say, you have a full data set and you want to automatically discover the feature. So you do not want to choose your feature. But we have the impression that this will not scale, that it's very difficult, that just based on the raw data, and the raw data are just the packets that are flowing in a node. Then you are able, in a scalable way, to do a good machine learning inference. And the existing solution for machine learning for networking, they are already based, for example, on flow level features. They are not analyzing the single packet. So I think that there is already this trend that you need to extract feature before you can run a machine learning inference. But I agree, it's a very interesting question, and it's a very interesting issue, because if you choose the wrong feature, then you lose the possibility of doing good algorithm. So I agree that is an open research issue. It's one of the open research issues that I mentioned at the end of the presentation.
Okay, maybe we can try some specific analysis on some use cases and see how we can do that separate feature extraction and the machine learning inference. Thank you.
Yeah.
We'll declare that we're on time, and that we can essentially close the meeting. You probably have seen that we requested a slot in London. I don't know who is going to be there in person. I know that myself won't be there, but we'll see. Hopefully people will be able to meet in person. I will still be virtual for a while. And so we will produce some notes. I took notes on the side. I will coordinate with Jeff about how we do that. And thank you very much to all the presenters. Thank you especially to people in Jeffrey's time zone, where it's currently extremely late. Thank you so very much, everybody. I really appreciate it. Jeffrey appreciates it. And again, Eve sends her best regards, and she's ill, so she couldn't join us today, but hopefully she'll be there, at least virtually, in London. Thank you very much. Thanks, Jeff. Bye, everybody.